Chapter 10, Section 10.3 will be the gas laws. We have Boyle's, Charles, Gay-Lussac's, and Dalton's laws. We'll start with Boyle's law, pressure versus volume. This is when temperature is constant. So pressure and volume are the only factors in Boyle's law. The relationship between pressure and volume is an inverse relationship. This means that as one increases, the other will do the opposite and decrease. So if we have pressure and volume, an increase of pressure would cause a decrease in volume, or the opposite, if we decrease pressure, that would cause an increase in volume. And that's an inverse relationship. You can notice this in the diagram that's given to you. As we increase the pressure from left to right, you'll notice that the volume gets smaller on the right. So here we will increase pressure, and then we'll see that the new diagram has double the pressure but half the volume. So here's another example. The graph of Boyle's law will look like a hyperbola. So increased pressure decreases volume. Here's another example of the graph not moving. And you'll notice that with our little examples here, the higher the pressure, the lower the volume. And then the lower the pressure, the higher the volume. Okay, some examples of Boyle's law. You can see a chart with the astronauts where as the pressure increases on the left, the volume of his suit decreases. And as the pressure is decreased on the right, the volume of his suit increases. Similar with the piston in an engine, where as you decrease the volume, the pressure is increased, and you can see it on the pressure gauge. And then the last one would be bubbles rising up from the ocean floor, and they're smaller as they're lower in the ocean, and then they get larger as they come up due to the decrease in pressure. Charles's law is going to be volume versus temperature. In this scenario, pressure is constant, so pressure is not a factor. There is a direct relationship between volume and temperature, which means that as you increase temperature, it would cause the volume to increase. Or, as in our picture here on the right, as you decrease the temperature, the volume also decreases. And so you'll notice that liquid nitrogen is being poured onto the balloon, which is causing it to become cooler, and therefore the balloon is getting smaller. So we are decreasing the temperature, and therefore the volume is increasing as well. So here's Charles's law. The graph will look like a straight diagonal line to show the direct relationship. And you'll notice here, they're keeping pressure constant. So as the volume is decreased, then the temperature increases, and vice versa. So here's an example of the graph, again, and then a balloon showing you that at 0 degrees, the volume is smaller than at 20 degrees where the volume is larger. Increased temperature increases volume. An example of this would be like a hot air balloon, where the temperature is actually increased, causing the volume of the balloon to increase as well. And then if the balloon is left to cool, then it would get smaller. Gay-Lussac's law is going to deal with pressure and temperature. Volume will be constant in this case scenario. There is a direct relationship between pressure and temperature, meaning as you increase temperature, like in this case, increasing the temperature under this tank, which is rigid and therefore cannot change volume, the pressure in the tank will also increase. And so the graph of this is a straight diagonal line, as you can see over here on the left-hand side, showing the direct relationship between pressure and temperature. Dalton's law is going to be the sum of all the partial pressures of all the gases in a sealed container. So if you have a container with more than one kind of gas, they each exert a unique pressure, such as in this example, where you have a tank of air on the right-hand side, but it's made up of oxygen, nitrogen, argon, water, and carbon dioxide. Notice at the bottom of each of the bottles, they each have a different pressure, but if you add up each of their individual pressures, it will equal the pressure of the air in the air bottle. Another example for Dalton's law is here, where they have helium on the left-hand side, 15 kilopascals, oxygen on the right-hand side at 15 kilopascals, but when they mix together, you can see that they end up only being 30 kilopascals, or they end up being a total of 30 kilopascals together. Another example over here on the right-hand side, you take the pressure of the first container plus the pressure of the second container and combine those two together to get the total pressure of the gases together. And so our equation for Dalton's law is the total pressure, PT, equals the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas, etc., depending on how many gases are present.